Possible causes of unbalanced phases include uneven loading on the three phases, power factor correction problems, transformer winding imbalances, loose or poor connections, and the open delta transformer configuration itself. Several potential solutions exist. Firstly, a line voltage regulator can stabilize incoming voltage fluctuations in balance phases. The cost can range from $1,000 to $5,000 per unit, depending on the capacity. Secondly, a voltage conditioner can filter out voltage spikes and regulate voltage within a specified range. These typically cost from $500 to $2,000 per unit. Thirdly, capacitor banks can improve power factor and reduce voltage imbalance. The cost is typically $200 to $1,000 per capacitor, depending on the capacitance. Fourthly, the utility company may be able to adjust the taps on the transformer to improve phase balance. This is typically a free or nominal fee. As next steps, firstly, document the phase imbalance. Monitor the voltage and phase balance over time to track the issue. Secondly, contact the utility company. Inform the utility provider about the persistent phase imbalance and request their assistance. Thirdly, consider a line voltage regulator or voltage conditioner. Explore these options if the utility company is unable to resolve the issue. Fourthly, upgrade motor protection. Install thermal overloads with higher trip settings or consider using electronic motor protection devices that are less sensitive to phase imbalance. Fifthly, negotiate with the utility company. Discuss options for mitigation or compensation if the utility company is unable to provide stable power. The 5% average, 10% maximum voltage regulation is a common industry standard, but may not always be achievable in practice. Open delta transformers are inherently prone to phase imbalance, especially when loads are not balanced. Phase imbalance can cause motor overloads, shorten motor life, and reduced efficiency. To elaborate further on the causes, consider that unbalanced phases arise when the voltage or current in each of the three phases of a three-phase power system are not equal. This inequality can stem from a variety of factors, each requiring a different approach to diagnose and rectify. Uneven loading is one of the most common culprits. If one or two phases are burdened with significantly more load than the others, it creates an imbalance in the current draw. This can happen in industrial settings where single-phase equipment is disproportionately connected to certain phases. Power factor correction problems can also contribute. Power factor refers to the relationship between real power and reactive power in an electrical system. Poor power factor, especially when not uniformly addressed across all phases, can lead to voltage drops and current imbalances. Transformer winding imbalances within the utilities transformers can be a more insidious cause. Manufacturing defects or degradation over time can lead to slight differences in the impedance of each winding, resulting in voltage and current discrepancies. Loose or poor connections anywhere in the electrical distribution system, from the utilities transformers to the motor control centers at the sewage pump stations, can introduce resistance and cause voltage drops that vary from phase to phase. The open delta transformer configuration, while cost-effective for providing three-phase power to relatively small loads, is inherently more susceptible to phase imbalance than a fully configured three-phase transformer bank. This is because the open delta design lacks the inherent balancing effect of a complete three-phase transformer. Moving on to the potential solutions in more detail, a line voltage regulator is a sophisticated device designed to maintain a stable output voltage despite fluctuations in the input voltage. It works by continuously monitoring the incoming voltage and adjusting its internal circuitry to compensate for any deviations, ensuring a balanced and consistent voltage supply to the connected equipment. This is particularly useful in situations where the utility power is prone to voltage sags or swells. A voltage conditioner, while similar to a line voltage regulator, typically offers additional features such as surge suppression and noise filtering. It provides a cleaner and more stable power supply, protecting sensitive equipment from voltage spikes, brownouts, and other power quality issues. Voltage conditioners are often used in critical applications where even small voltage fluctuations can disrupt operation. Capacitor banks are used to improve power factor by compensating for the inductive reactance of electrical loads such as motors. By reducing the reactive power demand, capacitor banks can minimize voltage drops and improve the overall efficiency of the electrical system. When properly sized and applied, capacitor banks can help to balance the voltage across the three phases, especially in systems with lagging power factor. Transformer tap adjustment involves changing the tap settings on the utility's transformers to compensate for voltage imbalances. Transformers typically have multiple taps that allow the voltage ratio to be adjusted slightly. By carefully selecting the appropriate tap settings, the utility company can optimize the voltage balance at the service entrance, ensuring that each phase receives approximately the same voltage. Regarding the next steps, documenting the phase imbalance is crucial for identifying the root cause and tracking the effectiveness of any corrective measures. This involves regularly monitoring the voltage and current on each phase using a power quality analyzer or a multimeter. The data should be recorded over time to identify any patterns or trends. Contacting the utility company is essential, as they are ultimately responsible for providing stable and reliable power. The utility company may be able to identify and resolve any issues on their end, such as transformer problems or distribution system imbalances. They may also be able to provide data on the voltage and current at the substation, which can help to diagnose the problem. Considering a line voltage regulator or voltage conditioner is a proactive step if the utility company is unable to resolve the phase imbalance. These devices can provide a stable, unbalanced voltage supply, protecting the sewage pump motors from damage and ensuring reliable operation. Upgrading motor protection involves installing thermal overloads with higher trip settings or using electronic motor protection devices that are less sensitive to phase imbalance. This can help to prevent nuisance tripping of the overloads while still providing adequate protection against motor overheating. Negotiating with the utility company may be necessary if they are unable to provide stable power. This could involve discussing options for mitigation, such as installing a dedicated transformer or upgrading the distribution system. In some cases, the utility company may be willing to provide compensation for any damages or losses incurred as a result of the phase imbalance. The 5% average, 10% maximum voltage regulation is a common industry standard that utilities strive to meet. However, it's important to recognize that this is just a target, and actual voltage levels can vary due to factors such as load changes, weather conditions, and equipment failures. Open delta transformers are inherently prone to phase imbalance due to their design. Unlike fully configured three-phase transformers, open delta transformers lack the inherent balancing effect of a complete three-phase system. This makes them more susceptible to voltage and current imbalances, especially when loads are not evenly distributed across the three phases. Phase imbalance can have several detrimental effects on electrical equipment, particularly motors. It can cause motor overloads, shorten motor life, and reduce efficiency. Unbalanced voltages can lead to excessive current flow in one or more phases, causing the motor to overheat and potentially fail prematurely. Furthermore, unbalanced currents can create torque pulsations, which can damage the motor windings and bearings. Finally, unbalanced phases can reduce the overall efficiency of the motor, leading to increased energy consumption and higher operating costs.